Okay, so I certainly knew about the Legendre polynomials. I certainly knew this property, and but I dismissed them from my mind because the Legendre polynomials behave very badly with respect to differentiation. If you take the derivative of a Legendre polynomial, it's not the Legendre polynomial 1 degree less. It's not even a nice combination of the other Legendre polynomials. So I didn't think that they were going to be useful, but Durand suggested that I look at them. And once you think to look at them, it really falls out very nicely. So here's the next theorem. Our mysterious polynomials Rn and Qn can be expressed really simply and beautifully in terms of the shifted Legendre polynomials. Right? So here it is. Rn of x is the sum, k going from 0 to n, of 2k plus 1 times pk star of x. Right? So R1 is 3p1 star plus p0 star. R2 is 5p2 star plus 3p1 star plus p0 star, etc. That's the expression for the r's, and then there's a similar expression for the q's. Okay, so now we'd like to, so all of our theorems at the moment are just conjectures, and now we'd like to prove them. Okay, so that's what we'll do. So the first thing I'm going to prove is this theorem 14, and theorem 14 is the one that says I really, that's going to be spacing quite a bit back here. Theorem 14 is the one that says I really do only have this one, right? Remember, calling it Qn of x was just a name, that I really do only have this one polynomial Rn of x, and otherwise d star is given by that. Okay, so let's prove that. And we're going to use the same strategy that we used before to prove that the adjoint didn't exist, except now we know that the adjoint does exist. Okay, so here it is. We know that d star exists. Again, we'll consider h equals d plus d star. And then we have the same computation we had before, that f of x on h of g of x is f of x d plus d star. So we get the same answer we got before. So f of x, calculation of g of x is f of 1 g of 1 minus f of 0 g of 0. And now I'm going to think about this formula. I'm going to let g of x be a fixed but arbitrary element of my basis e, and I'll let f of x run through every polynomial in Pn of x. So suppose g of x is the function 1, right? The 0th element of my basis. Well, then g of 1 is 1 and g of 0 is 1. So I get that for every f of x, this inner product is f of 1 minus f of 0. But if g of x is any positive power of x, right? X squared up to x to the n, I still have this formula, but notice that for any positive power of x, g of 1 is 1 and g of 0 is 0. So for every positive power of x, I get that this is equal to f of 1. So what does that say? It says that for k going through 1 to n, this capital H of g of x, if they all evaluate the same against every polynomial in my vector space. Well, non-singularity says then they must be the same. So that says, right, so it says that capital H of x is the same as capital H of x squared up to capital H of x to the n. They're all the same, and that's my polynomial R sub n of x. And then d star is minus d plus h, so there it is. The derivative of x to the k is minus k x to the k minus 1. Right, that fact comes from the derivative plus R sub n. So that, right, so there's the common value of R sub n of x for all of these. Okay, and I'm going to use this again, so let me just restate it here. This says for every f and p sub n of x, this common value here is what I'm calling R sub n of x. So f of x evaluating as R sub n of x is this, which is just f of 1. Okay, so now we know we only have a single polynomial R sub n of x to figure out, and now the question is, how are we going to figure it out? Okay, and so we're going to express it in terms of the Legendre polynomials. So we have this we have the theorem that I gave you before is simply a recursive expression. Right? It says that R1 is 3p1 star plus p0 star, and then Rn here is Rn minus 1 plus the next term, which is 2n plus 1 pn. So this is the recursion I'd like to prove, and we'll prove this recursion by induction. So by induction, you just check that R1 is given by that. That's easy. And then otherwise, we look at this last corollary here. Okay? And now, suppose f of x has degree at most n minus 1. Well, of course, if f of x has the degree at most n minus 1, it's in Pn of x. So we get this answer. But it's also in Pn minus 1 of x. So I can replace the n by an n minus 1 here, the n by an n minus 1 here, and get this, and here as well, and get the same answer. So what that says is that for every polynomial of degree at most n minus 1, the value of f of x against Rn minus 1 of x is f of 1. That's also the same as the value of f of x against Rn of x. In other words, if we look at the difference, Rn minus 1, that's orthogonal to every polynomial of degree at most n minus 1. Okay? Well, but the polynomials of degree at most n minus 1 are the span of all of the shifted Legendre polynomials from 0 up to n minus 1. And that's an orthogonal basis. Right? So if this polynomial is orthogonal to everything in here, we have an orthogonal basis, it must simply be some multiple of the last basis element. Okay? So I have that this difference is c times p sub n star of x for some constant c, and now my question is, how am I going to find c? Here's the answer. I'll use this equation here, but for Pn star. Right? I said that Pn star of 1 equals 1. Right? That was one of my properties of the Legendre polynomials. So I'll put Pn star in there. Okay? If I put Pn star in there, right, that's the value of Pn star against Rn. Rn is just this. And now I apply linearity, and that evaluates 0 because this is polynomial of degree of most n minus 1, and Pn star is orthogonal to it. So that's just going to be the value of Pn star against C Pn star. I have linearity, I can pull the C out in front. That's going to be C times the value of Pn star against Pn star. And again, I told you that the Legendre polynomials are orthogonal, and the value of any Pn star against itself is 1 over 2n plus 1. So I simply get this equation, 1 equals C over 2n plus 1, so C equals 2n plus 1. And that proves this recursive expansion for the R's. For the Q's, you get a very similar sort of recursion. It's proved by exactly the same ideas. But let me just remark why you see, you get this 1 plus minus 1 to the n. The minus 1 to the n is coming from the fact that when you look at the value of the shifted Legendre polynomial at 0, right, there's that sign 1 plus minus 1 to the n. And if you go back to this theorem, and you think about this recursion here, right, if you're looking at 2m minus 1, 4k minus 1 is 2m minus 1 times 2 plus 1. Right? There's that there. So it says when you go to the next stage, you either multiply by 1 plus 1 or 2, or 1 plus minus 1, which is 0. So that accounts for this 2 here and for the implicit 0 every other time. Okay. So we now know how to express our polynomials Qn and Rn in terms of the shifted Legendre polynomials. Now we'd like to get our closed form expression. Well, we have a conjecture for what the coefficients of R sub n are. We have an expression in terms of the shifted Legendre polynomials, and we know what the formula for the shifted Legendre polynomials are. Right? So we have some conjectured equality, which says some coefficient on the left-hand side, which we've determined experimentally, is some linear combination of known coefficients of shifted Legendre polynomials. So we have some conjectured combinatorial equality. So we look at this equality, we simplify it a bit, and we see that that equality is equivalent to these identities, where this identity for a particular value of n and I says that the coefficient of x to the I in R sub n of x is what we think it is. Okay, so this is true since R sub n has degree n, I goes from 0 to n, so I can turn this around and say this is true for every I greater than 0 and n greater than or equal to I, and then I have a combinatorial identity, which is very easy to prove by induction. It's absolutely a straightforward induction that takes half a page. So induction says then that our coefficients are exactly what we think they are, and that finishes the proof of our theorem 14. Theorem 15, which is the one that gave us the exact values. Okay. Right. So that finishes this part of the talk, and since I do have some time, I'm going to derive something else here. Okay. So using this work, we can get these much more elaborate set of combinatorial identities. So here's a very elaborate set of combinatorial identities, and these are true. How do you get these? Well, first of all, let me say that if you suppose you let n equals 0, okay, you still get something complicated, but if n equals 0, it simplifies. And it simplifies to this much pretty and nicer looking identity. I gave this to a student, and he used the Wolff-Zalberg method to show that it's true. But there's one thing you might think. If you have something, these signs alternate, and this is equal to 1, you might be tempted to put all the negative terms over on the left side, and then you might think, well, you're counting something, right? In one way, you count everything, and another way, you count everything except you miss one. So there should be some nice combinatorial interpretation. Well, if there is some nice combinatorial interpretation, it's not easy, because here are what the coefficients look like for various small values of n. And you see, there's no sort of term-by-term cancellation. I mean, it is true that 1 is the sum of all these numbers, but there's no nice way that some of them cancel against the others. So I don't know any nice combinatorial proof of this, and I don't think there's some nice bijective proof of this. I think that just is a more complicated identity. So
can you scroll up, please? Scroll up, I want to see this. I think it must be nice. It must be an excellent proof. It's still nice not to have one.
actually, this is in the paper you have a copy of.
Okay. Right.
Okay, so let me say how we prove this, and then I'll tell you some more things that Duran told me. Okay, so let's consider an arbitrary polynomial here, and let's look at this integral here. So that's the value of this polynomial against x to the j, right? So what's this here, right? Okay, so we have simply this here. Okay, now remember that Rn of x is determined by its value against every function f of x is 1, so that's certainly true against every polynomial x to the j. Right? Okay, and now if you think, suppose we write R sub n in terms of coefficients, and we simply do this, a little work shows that you get a system of linear equations where the coefficient matrix k sub n is once again the n plus 1 by n plus 1 Hilbert matrix, again with the entries numbered from 0 to n. The right-hand sides are all 1, that's all of these 1s here, and the d zeros are these coefficients here. Well, if that's true, that says the d's, there's k sub n inverse times this. But we know what the d's are, right? The d's are the coefficients of R sub n, which we've already determined. So and we know what the entries of k sub n inverse are, right? These are the entries of the inverse of the Hilbert matrix. So applying what we know, that simply says that here this complicated expression on the right-hand side is the ij entry of the inverse of the Hilbert matrix with our number in. And so if we apply this, the left-hand sides of these are the coefficients in R sub n of x, and when we apply this, we get when we apply this and simply multiply out, we get these identities. And as Duran pointed out to me, these identities are actually not new. They're very old. They follow from the classical Fausch's hypergeometric function identities. And Duran also said that I mentioned the Wolff-Zalberg method for the case n equals 0, which I gave to a student, but they follow from his method as well. So that's what I wanted to say, and thank you for your attention.
A beautiful experimental talk and also both. And we have time for some questions. So I wonder if you can generalize this beautiful theory is a more generalized version of Legendre Gegenbau. Then you have Jacobi with different weights.
Right.
I wonder with this beautiful hue we might extend
Right.
to other orthogonal polynomials.
Yeah. So of course the answer is. Is this cool that?
Yep.
Yeah. The answer is I don't know, but there is something. It's not just in this case. It's simpler. There's really something different going on. So let's call. So all these comes from integrals over some interval of f of x, g of x times some weight, right? A to b. Okay, so let's call this fg sub w. Okay, for the weight w. Well, what this uses, if you look at f of x, g prime of x, plus f prime of x, g of x, that was the integral, in our case, right, of f prime of x, g of x, dx, plus f of x, g prime of x, dx. Right, and so that becomes the integral from 0 to 1 of the derivative of f of x, g of x, dx. Suppose you put a w in here. Put a w in here and a w in here, you get a factor w of x in here and w of x in here. And so this no longer becomes a derivative because you have another term, right? You have the integral here with the w of x is this plus the integral from 0 to 1 of f of x, g of x, w prime of x, dx.
Oh, so maybe you need a generalized derivative or some analog derivative.
Right. So what this becomes is it becomes f of x, g of x, but with a different weight w prime. So in this case, w prime is 0, and you don't get this term. But this term. So in the more general case, you get this really interesting sort of behavior where you start with one inner product, and when you express the adjoint, you involve a different inner product. So that really has a more involved character, but it's a really interesting question, and I don't know the answer to it. But it's certainly something to investigate.
Let's thank Stephen again.